Right. Oh, there we go. I hit that twice, so I think my computer's waking up. No, it's going to stay there. The bedrock, geology of British Columbia, 7% of the bedrock is made up of Alldrick rocks, early Jurassic age Alldrick rocks. That's all those green blobs you can see through there, through the whole of British Columbia, extending down into Vancouver Island. And in different parts of British Columbia, they're given different names, but up in the northwest they're known as Hazelton Group. And there's a red ribbon. Oh, could someone turn the lights off, please? It'll be easier to see these colors. Yeah. And there's a red ribbon that's wandering through there in the Hazelton rocks, and that's 250 kilometers long, and that's the interpreted trace of the Eskay Rift, and you can see it plotted on that other map as well.
That cuts across the Alldrick Basin?
No, it runs along the west side, the west rim. The band is so wide that it's actually, you can't see the green rocks underneath it. But it's around the western rim of the Bowser. The Bowser Basin is that big white spot off to the right. Oh, I should be using this. There we go. Right. So we had a project area to study the northern part of the Eskay Rift, and the reason we were concentrating on the northern part is that the Geological Survey of Canada, from Bob Anderson, worked on the central part, and Carol Levichik and later on did some work in the southern part of the Eskay Rift. It was the northern part that was least studied or unstudied and deserved more work. And then, having done that work, we were able to come back and reassess the geological work that had been done on the southern part as well. Through the 3 years of the program, we produced 4 different maps and 6 reports, and all this information is available to you free over from the BC Geological Survey website. The story starts with the discovery of the Eskay Creek deposit in 1988, but by 1990, Bob Anderson, both in a written report, a short progress report, and in a lecture, produced this study on the left, which is he lined up about 23 different patches and pieces of pillow basalt rocks that were in the literature and things that he had mapped during his work in the central area. The Eskay Creek deposit sits right there, this tiny little shred of pillow basalts. And he said all these rocks are really unusual because they're sitting at the top of the Hazelton group, and pillow basalts are unknown within the Hazelton. And they're all of similar age, they're a similar character, and he thought they represented something that accumulated in a long linear trough or a rift structure. So that was his original interpretation. We moved forward into 2002 when Carol Levichik and Vicki McNichol had done studies down further south in Georgia River. Those are off to the south on this map. Georgia River and Antioch's Pendant, they've done some mapping in those areas, concluded that the pillow lavas and the rhyolites, in case of Georgia River, that they saw in those rocks were, again, sitting at similar stratigraphic positions, similar age, unusual features in the Hazelton, and that gave them the confidence to extend the trace of the Eskay Rift from this pattern that Bob had recognized, but they didn't put any bounding faults on it, and they postulated these interpreted bounding faults, these 2 red bands, which are the 2 sides of the rift structure. So all the rocks in the center dropped down, accumulated those pillow basalts. And these are interpreted boundaries because at the time this paper was published in 2002, no one had seen these bounding rifts in place, these bounding faults in place. So you're now looking at 250 kilometers of strike length and 25 large and small segments of preserved stratigraphy. The reason the Eskay Rift is important is that within it there are some 75 mineral occurrences. Those are showings, prospects, deposits, past producing mines, and the active mine at Eskay Creek. I've summarized this in really simplistic form, all 75 of these. Within the ore deposits, there's 22 of these. 10 of these are down in the Antioch's Pendant, where Hidden Creek Mine produced from 8 separate sulfide lenses. Bonanza Mine produced from 2 separate sulfide lenses. Up at the Eskay Creek Mine, this is historic mining, up in the Eskay Creek Mine there are 12 separate ore zones defined and held in reserve calculations. They may not produce from all of them, but there are 12 separate ore zones. In addition to that, if that's 22, then there are 53 mineral showings to get to 75, and there may be more in the Eskay Creek area because we don't have all the confidential data from Barrick's records and Homestake's exploration work, but at least 53. I've shown these as single dots here in yellow. So there's 8 mineral showings summarized or symbolized there up at Table Mountain. 35 plus showings in the Eskay Creek area. We'll look at this in some detail later. another 4 down at the Mount Madge area, and Georgia River and Antioch. You'll see that in this diagram, the Eskay shred or segment of pillow basalts is separate from Mount Madge, and later on we'll make the point that these actually join up when you include not only the basalts, but the rhyolites and siltstones that are also part of the rift fill sequence. So this is an incredible, over 250 kilometers of strike length in the rift. You've got 75 mineral occurrences. The reality is, if you just look at the erosional remnants of these rift rocks, here, here, and here, and add up the lengths of the exposed, you've only got about 60 kilometers of exposed strike length, erosional remnants left. There's a lot of places here where there's no rocks left. So you still got the same 75 mineral occurrences in just 60 kilometers of exposed bedrock, exposed rift fill sequence, which is an incredible density of mineral occurrences. The question is, why is the Eskay rift so well mineralized? And the answer is that it isn't. All rift structures have this ability to concentrate and to be this well mineralized around the globe. And the reason is that the same processes and features that are characteristic of the formation of rift structures are also essential components of the formation of hydrothermal mineral deposits, either exhalative deposits, the VMS type deposits if you're in a subaqueous setting, or hydrothermal epithermal type mineralization if you're in a subarea setting. And I summarize all those characteristics and processes in a list I call the High Five list. Rift structures are zones of high permeability, high fluid flow. That's because they have these deep bounding faults that run deep into the crust. And because the center part of the rift drops down dramatically, so you get areas of high relief, so you get high energy sedimentation filling in the rift, you get high preservation rates. In fact, you really get a total preservation rate. You're looking at 100% preservation. The rule of thumb is that what happens in a rift stays in a rift. There's nowhere else for the material to go. These are zones of high heat flow because you get shallow magma bodies and dikes working their way up these deep bounding faults. They are, because some of that magma reaches the paleosurface, are areas of high volumes of volcanism, and the volcanism is characteristically highly fractionated. You get basalt rhyolite end members. You don't see the intermediate andesite-dacite compositions. And that comes into play a little later as well. These are two cross sections through a rift. The upper one is a laboratory model, but the lower one is a real section through the Central Europe, the Rhine Graben. A couple of features I'd like to emphasize here: that the bounding faults of these rifts tend to dip inward at about 60 degrees. You can get minor mirror image faults called antithetic faults running in the opposite direction here. Lots of complex faulting. Note that whether it's real or in a laboratory, that this central block doesn't drop down nice and level like the floor of an elevator. It founders or collapses in an asymmetric fashion. And what that means is in different parts of the rift, you're going to get different thicknesses of the rift fill sequence here. This stratigraphy is thicker than the same rocks over in this area because the floor of the rift has dropped down further in that area. And the most intense faulting, although there can be faulting all through this structure, is near the margins where the main bounding faults sit. We can look at an active rift. If we go to area Ethiopia just west of the Red Sea, this is at the northern end of the Great African Rift, the Central African Rift structure. And what we're looking at here, because I want you to see the nature of this complex bounding faults here. There's a scarp surface here that's all covered with talus and debris, and that is the outer earliest fault that was the bounding fault. This is just one side of a rift structure. One edge, one bounding fault area. So this block slid down relative to this one along this fault surface until it locked. It only slides a certain distance, and then the whole thing freezes and locks, and then the rocks fracture again inboard, always on the inboard side, and they begin to slide again, and you see all this talus and debris accumulating in a little bit of alluvial fan there. And this slid again until it locked, and here's the next scarp over here. The rocks cracked again because the rifting hadn't finished, but the movement on that particular scarp had finished, rifted again and fractured, slid again. You can see the talus blocks dropping down here. And while all of this was going on, magma was working its way up these bounding faults, these rift structures, well, not rift structures, but these fault structures. And some of it extruded on surface, so you have these huge floods of basalt that covered the basin, the rift floor, extending up here. That's an older one. You can actually see the edge here where a younger basalt flow has overridden an older basalt flow. So these were extruded virtually yesterday. And the question is the rifting finished now? Well, it hasn't finished, and I've got a newspaper article about new rifting that's gone on in exactly this area. But here you can see a crack, which is yet the next. So we're looking at 1, 2, 3, 4 faults that have all occurred in sequence, always moving inboard from the original fault out there. So this rifting is continuing. You can also see cinder cones and a phreatomagmatic crater in this area. There's a shaded scarp here, and this is one of those 60-degree in the opposite direction antithetic faults, breaking the other way and coming in and joining these major boundaries. That's a lake up there, a salt lake. This is an arm of the Gulf of Aden or Red Sea that's coming in this area. It's flooded the area. So this region is subaerial, rifting through here. This is subaqueous. In a larger scale, things along these fractures and faults at depth, you would expect to look for ectothermal mineralization, not on the surface, but at depth along these fractures. In this setting, you'd be looking for exhalative mineralization that reaches the seafloor and deposits syngenetic sulfides. So all of these components are exposed in this one photograph.
So is that cinder cone acid rocks?
Are they?
Acid rocks?
I'm not sure there.
Okay.
But I've got a newspaper article showing where there's both basalts and rhyolites exposed together north, about 40 kilometers north of that photograph.
It's a great
along those same fractures.
Yeah.
The reason we picked that as an example is because it's rifting today. All of that's happening right now in Africa. And as recently as last year, it was a newspaper article about, wow, it's a trade paper. In any case, before we get into the details of the Eskay rift, to appreciate why it's unique and so easily recognizable, we have to talk about the rocks that sit around it, the Hazelton Arc Passage rocks. If you've got time concerns...
no time concerns,
okay.
Nothing.
So we're going to look at the Island Arc rocks, the classic Island Arc rocks that are typical of Hazelton. We've got about 5 kilometers in thickness. They span the whole of the lower Jurassic, so they run in age from 200 million years to 175. See a date there, 176, 175. So 25 million years of geologic history preserved in 5 kilometers of stratigraphy. The lower, most dominant component is variably textured, variably porphyritic andesites, mostly subaerial in the Stewart region. Then they're overlain by volcanic conglomerates. There's a period where erosion supersedes volcanic extrusion. So you're seeing more erosion, the products of erosion, volcanic conglomerates, sandstone, siltstone, with interbedded andesites and even some dacite. And then the final episode is a thin but widespread dacite blanket, pyroclastic blanket, the last volcanic event that happened regionally in these rocks were several local sites of high energy, catastrophic dacite volcanism that blanketed the area with proximal deposits near the beds and then distal dust tubes further away. You get welded tubes and all these things. About 176 million years. In contrast to that, over in the rift, you have the rift fill sequence spans the age from just 176 to 174 million years. So it's only 2 million years of geologic history preserved in this rift, but it can be 2 to 3 to even 4 kilometers in thickness. And so that you should recognize that you're looking at 25 million years of geologic history here preserved in 4 to 5 kilometers of thickness, and 2 to 4 kilometers in thickness here preserving just 2 million years of geologic history. And the difference is, of course, that what happens in a rift stays in a rift. You've got a completely preserved geologic record in here because everything that deposits in that rift basin stays there. On this volcanic summit, everything that deposits there is prone to erosion and be weathered away. So this is, as this volcano, this particular volcano is building, it's also being eroded away and topographically depressed. The rift-fill rocks are characteristically 3 units: basalt, rhyolite, and siltstone. They're so predictable, so reliable, I call them the Eskay Trinity, these 3 rock types. Now there's still lots of flexibility possible in there. You can stack these rock types in any sequence you want. You can have multiple layers of basalt intercalated with multiple horizons of rhyolite and siltstone. You can have varying amounts so that siltstone is the dominant lithology in some areas. Rhyolite might be the dominant lithology in some erosional remnants of the Eskay Rift. And in a couple of places, like Antiochs, one or the other of these units might be missing. But still, this is a dramatic contrast difference between this stratigraphy and this stratigraphic interval or age interval 176 to 174 would be equivalent to just the uppermost part of this entire 25 million year history. So just these rocks up here. There's a question mark down here, and that's just there to remind me to mention that it's not that we don't know what sits in the floor of the rift, that it's highly variable. The rocks in the floor of this rift, the rocks that existed before the rifting started and the floor dropped down, the pre-rift stratigraphy here can range and vary in anything from the uppermost part of this stratigraphy in here, and that's what you see at the Eskay mine. It can be rocks of the lower andesitic units of the Upper Hazelton. We can see upper Triassic Stahini group rocks here in the floor of the rift. And in one case, we actually see Paleozoic Stikine assemblage stratigraphy sitting in the floor of the rift. So these rocks are sitting on a Stikine assemblage, highly metamorphosed Paleozoic basalts and limestones. So lots of variation down there. Once we recognize the dramatic difference between this stratigraphy and this stratigraphy, we realize there's something quite unusual going on in just 6 little areas, and by little I mean areas of about 1 to 2 square kilometers, very small areas and very small stratigraphic intervals, 100 to 200 meters total stratigraphy, so this is a very small piece. In fact, it's probably exaggerated there. In these small areas, and there's only 6 of them that we recognize, we find these rocks, which are totally different rocks from this package, actually interfingered and intercalated with this rock package. So you're actually seeing a mix. It's like taking a black deck of cards, colored black, and a red deck of cards, and just taking the corners and shuffling them together so that they're on lap with each other. And we see detailed, very thin units of basalt, rhyolite, but also dacite and volcanic conglomerate and siltstone all intermixed in here. And recognizing these, what we call near rift units. Well, first of all, I better tell you how we think they formed. We think these near rift sections formed in this situation before rifting began. Before rifting began, you had a block of ground, wherever it might be, somewhere in an island arc setting, and you're depositing dacites, andesites, and conglomerates, particularly at the last part, the upper part of that island arc succession there. These intermediate volcanic compositions. But at some point, there's a rift structure, one of the bounding faults of rift, working its way up from below. And in some one place, that fault is going to break surface first. Oh, I pressed the wrong button. There we go. It's going to break surface first. And at that location, don't forget that along with the faulting, you've also got magma bodies working their way up these faults. And the minute you break surface there, you remove the lithostatic cap, the confining pressure. The magma rushes to surface. And we see an immediate outpouring of rhyolite. The first rock we find in all these exposures to these areas in near rift sequences is always rhyolite. Not in huge volumes, because even aerially you're only talking 1 or 2 square kilometers. But rhyolite first, and it's immediate. While that eruption is going on, that fault is continuing to work its way up, but also now continuing to work its way sideways, laterally along, propagate along strike, as they say. Volcanism continues, but at some point, this fault propagates far enough that it detaches. So now you've detached this block, or rather this hanging wall block from the footwall block, and the thing's going to start to slide. The moment this block, because of course there's another bounding fault somewhere over to the west here that's doing the same thing. The moment this block begins to subside, this volcanism stops abruptly. And the reason it stops abruptly, so you've got movement along that fault finally because it's become long enough that the 2 blocks can unhinge. The reason it stops abruptly is because all further volcanism is happening down here on this surface at this contact. Volcanism continues because there's lots of magma running up. You've got more magma flowing up this active moving fault than you did when it was static, when it was just a crack in the ground. So you get rhyolite, you get basalt, you get the siltstones accumulating in there, and you've left a small piece of rhyolite and probably some basalt, but also these dacites and andesites, conglomerates getting washed in from wherever the island arc volcanic center, the nearest one happens to be. It's washing material in there. So for a short period of time, while this fault has been forming and propagating, you've got intercalations of these 2 disparate, totally different rock types accumulating together. The other thing we found in one area, we believe that because this rhyolite pile gets cut off by an inclined fault, I think we actually see debris from this rhyolitic rock accumulating on the scarp face down there. So recognizing we'd seen these rocks as much as 18 years ago, But recognizing what they represented, they were a puzzle to us, and we knew it was something different. But it's taken all this time to realize what they represented. So recognizing them has been a real revelation. And what it's revealed is that we've got a problem with the Eskay rift, with the interpreted trace of the Eskay rift, with its location. Because if we plot up those 6 areas of near rift sequences, these are packages of rock, small in area, small in thickness, small intervals, that should be sitting adjacent to the bounding faults of the rift, but immediately outside, immediately outboard of the rift. We find that we've got a couple of these packages of rocks here at Arctic Grid and here at Bruce Glacier, which is just east of the Eskay mine, that are fitting in exactly where you'd like them to be on the outside of the bounding faults of the interpreted trace of the Eskay rift. We've also got 2 areas at Logan Ridge and Class Line Plateau that lie within the rift structure. And then we've got another 2 that are gone completely walkabout. They're tens of kilometers away from any interpreted rift at all. One at the northwest edge of Weechee Dome, one at Tim Williams Glacier. These are really similar looking sequences, thin layers of basalt, rhyolite, andesite, dacite, volcanic clastic conglomerate, and there they sit. So that's a problem to start with. As long as I'm sharing my problems with you, we've got a couple more. Here on the southeast flank of Mount Zaidza in the 1960s, Jack Souther mapped a significant area of siltstones with intercalated basalt and rhyolite, minor volcanic components, but a big thick section of siltstone. So all the rocks in that package are Eskay rift fill type rocks rather than classic arc rocks. Good fossil constraints. You've got good fossil collection on siltstones. They're unquestionably Eskay rift age stratigraphy right at the lower Jurassic, middle Jurassic boundary. They call it Toarcian-Elenian boundary when you break down into biostratigraphic terms. That's the age of that rock package, and it would be nice to see those rocks within the rift boundary, but at the moment, as the rift's been interpreted, they sit there. And finally, the biggest problem of all is in this area at Snowball Creek, which is just south of the Hank epithermal deposit, or the Mary porphyry deposit, if you're familiar with those. There's a large, broad area, recently glaciated valley, quite wide, beautiful rock exposure, superb, extensive rock exposure of hematitic, epiclastic conglomerate rocks with intercalated andesites and dacites, one thin distal rhyolite tooth unit, and then overlain by fossiliferous sediments. We've got good fossil constraints from collections by both Jack Souther and Carol Levenchick that tell us that this is right at the top of the Hazelton, last uppermost Hazelton, and these rocks are classic arc rocks. These are not rift fill rocks, and yet there they sit in the middle of this interpreted trace of the rift. So we've got a lot of problems there, and after trying to invent faults and know and map to move this piece of terrain into the center of the rift, it can't sit in a rift, it's arc facies rocks. The obvious conclusion is we had to take the Eskay rift back to the drawing board and look at our assumptions in creating these boundaries in the first place. So there's that diagram, the interpretation of the Eskay rift as of 2002, and here's the new interpretation. There's 2 parallel rift structures. Although this looks dramatically different, you appreciate right away that, first of all, the southern 2/3 of this structure here is exactly the same as this structure here. We've added a western margin to the rift because what we found in the 3 places where we've discovered the bounding faults of the rift in outcrop is that they're right up adjacent to the rocks themselves that are rift fill sequences that are exposed in the rift fill, at the margin of the rift fill rocks. They're not tens of kilometers away or even a few kilometers away as some areas in here suggest. So they're tucked right up close against the rocks. So we learned that lesson. Secondly, this still respects Bob Anderson's original definition of the Eskay rift as a long linear fault-bounded trench or trough, the rift structure. This original interpretation, 250 kilometers long. Cumulatively, we're now looking at 450 kilometers strike length over these 2 parallel rift structures. There's a young fault here called the Forest Curve Fault that cuts everything off. The rocks exposed off to the west are much lower in stratigraphy. They're Devonian age intrusions and Paleozoic stratigraphy. So if the rift, this part of the rift ever extended further to the northwest, it's eroded away. But you see by this new interpretation that we now have all our ducks lined up. These near rift stratigraphic packages are all sitting immediately adjacent to the bounding faults of the rift, but outboard, here, and this one here. We've managed to fit Jack Souther's area of siltstones, upper Hazelton siltstones, and thin rhyolite basalt flows into the rift structure. And most important to me is that this block at Snowball Creek is now outside the rift structures, but given that it's so close to the rifts, it's perhaps not surprising there's a thin rhyolite tooth unit preserved within that otherwise arc stratigraphy. Well, perhaps it's not surprising that this new interpretation fits all those features that we try to accommodate, because we essentially erased the old rift structure and started drawing lines on the map to make it fit. But the real test of this is to see if any of the other geological features, geological questions that we know from our mapping in this area also fit or help to support this interpretation, and indeed they do. The first thing to emphasize is that in 2003, Joanne Nelson and Kirsty Simpson were mapping on the west side of Table Mountain here, and they found the first exposure, one of these bounding faults of the rift bounding faults. Now it's written up in our reports and described. We didn't make a lot of noise about it. It should have been a huge achievement, because when they found it, it was actually a bit of a problem for us, because it was a structure that was tucked right up against it has pillow lavas on the east side, and on the footwall side it has fragmental andesites, Hazelton andesitic fragmental tooths. But the problem was it was striking about 45 degrees. You'll notice the north arrow is a little bit off, cranked around to the east there. It was striking about 45 degrees west to north, or striking northwest, dipping to the east. But at that time, we believed that the bounding fault of the rift was somewhere off to the west and striking, frankly, a little bit east to north. So this was off at about 40, 45 degrees different strike from what we were expecting to find. And when that was, so we didn't really know what to make of this clear bounding fault that we discovered. But it makes perfect sense with this new interpretation. In addition, in 2005, Alex Wallace was prospecting at Surprise Creek, so that's just north of the Highway 37 at Bear Pass as you head into Stewart. And he found rhyolite flows, a succession of rhyolite flows, 50 meters or more, a sequence of rhyolites with interflow magnetite. And I've seen those exposures this summer. And Alex was most interested in the magnetite and to find out if it carried any gold at all, and wanted to know if I'd seen any magnetite before. And of course the answer is in Hazelton rocks, and no, I had never seen strata-bound magnetite. But I'd seen a little bit of rhyolite, and I knew that whenever you found rhyolite, you're in an proximal position adjacent to the rift. So there's a thick succession of rhyolites there, preserved as well. And in 1987, following a field season of work in the Kitsault River Valley, Jerry Blackwell came up to me, because he was aware, he already realized, as we had from our work in 1985 in Kitsault Valley, that the uppermost rock unit preserved in the Hazelton rocks in the Kitsault Valley is that regionally distributed dacite pyroclastic. It's a blanket of dacite fragmental and distal tubes, welded tubes and such. But in Iliance Mountain, which is a significant peak in the area, it's a resistant hilltop of rhyolite. It's different. It's not the dacites. It's a rhyolite unit. Several units or extrusive units there. And he said it's different than anything he'd seen anywhere else in the valley. And he thought I ought to go look at it. And still, you have to get there and have another look. Have a look. But that unit is rhyolite right there, whereas most of the other rocks at the top of Kitsault, adjacent to the Bowser Basin rocks, Bowser Lake Route, is dacitic rocks. In addition to that, there are a series of mineral occurrences here. This is called Leftover Yankee Boy, and these are on your LGY plane block?
It's not ours.
It's not yours. Okay.
Just to the west of ours.
All right. Leftover Yankee Boy are described in the literature in Minfile as hosted in pyritic rhyolite, so the entire host unit is pyritic, and these are both cross-cutting veinlets and strata-bound semi-massive sulfide mineralization that has elevated values of copper, lead, zinc, silver, gold, and mercury. So these deposits are sitting in rhyolite at the top of the Hazelton in this location. Over here in the arc rocks, we're outside the rift, in these arc passage rocks, we've got a series of unusual breccias that are located near the Kitsault Lake strata-bound lead zinc silver prospect. That's in limestone near Kitsault Lake, but in the vicinity around that there are barite breccias, barite veins with class of wall rock in them. And there's also one small area of orpiment veining in these rocks. So these are unusual as well. They're more epithermal in character. So there's several features. Oh, the other point I wanted to mention is that with this interpretation, just north of this block of ground, or rather this piece of ground, is a block that hosts the GJ, Kinscan Lake porphyry copper deposit. Porphyry copper gold is being drilled currently. Major deposits, many years, decades of drilling. This interpretation would suggest that in the area where they're drilling Triassic rocks, their mineralization is in the lower upper Triassic rocks, below the Hazelton, is that they're somewhere down in the floor of the rift, and they're really not, this story shouldn't concern them at all, except that they do find a lot of minor faults jostling up their stratigraphy, and that's a problem, and luckily they're drilling something that's a bulk tonnage target, so the minor faults isn't quite as big a problem as it might be for something in the stratabound. So that's where they thought they were sitting. However, with this new interpretation, this puts the bounding faults of the rift somewhere off to the west. Their big porphyry system is here. They're sitting up on the plateau, and that doesn't really affect them, except as they're drilling further and further west, they have to drill through cap rock of Hazelton stratigraphy now. Their strata dips southwesterly, so they're drilling, as they move westward, they're drilling through some of the cap rock to get into their mineralized Triassic porphyry system down below. What they find as they go west on their plateau is they're starting to cross north-south trending faults that are downdropped on the west. And it's like going down a staircase. They drill in westward on their grid, and suddenly they're drilling deeper holes than they ever had to before to hit their mineralization. Mineralization is still there. In fact, it's teasing them because it's getting better grade and longer intersections. But they move west again, and they cross yet another one of these parallel north-south faults, and it's downdropped again. So they're going down the stairway, and their porphyry mineralization is getting further and further out of reach of depth. So they're the only people I know that don't like this interpretation, because it means that the western edge, as their porphyry grades and continuity are increasing, it's getting deeper and deeper. And that's as new as this summer's drilling. Oops. I pressed the wrong button. Oh, I wanted to emphasize something about a few of the features about mineralization in the not mineralization, about the geology. Some of the things we learned about this geology, and this is where we pull in the work by Carol Emchick and Bob Anderson. We're going to look at talk about three different areas here, those three yellow dots. In the six-pack range area, just north of Pillow Basalt Ridge, this is where the rocks of the Eskay Rift sit on a downdrop rift floor sequence of Paleozoic rocks. They're perched up on Paleozoic stratigraphy, and these rocks this rift fill sequence is entirely subaerial. It's coarse clastic sandstones. They're chaotic. They're rounded pebbles to subangular to angular fragments. It's high energy. It's not well sorted. It's subaerially deposited alluvial fans, sandstones, very little mudstone or silt. There are major basalt flows sandwiched into this sequence, stacked within the sequence. They are not pillowed. They're massive flows. They're tens of meters thick, and they're just solid crystalline basalt. And there are also minor, thinner rhyolite flows within that succession. So it's dominantly in character, it's sandstones and pebble conglomerates to, well, barely cobble conglomerates. And so it's a thick succession, high energy, but aerially deposited. When we get to the Eskay deposit, there's been a series of studies on exactly what the water depth was. And when you look at the earliest, which there's 12 different mineral zones there, the earliest formed mineral zones, which is the veins down in the footwall rhyolite, those earliest formed mineral zones from the fluid inclusion data were shallow water deposits. They're deposited in shallow water, even sub-aerial settings. They believe it's shallow water. And that's like the 109 vein. They've got depths of 50 to 100 meters water depth. Whereas the newer, most recent deposits that are part of those 12 different mineral zones at the NEX and hanging wall zones are stratabound syngenetic mineralization formed at the seafloor. And those are deeper water. So what it suggests is that the floor of the rift was actually, during the time it took these 12 different mineral deposits to form at different stratigraphic positions, the floor of the rift was actually dropping down as this mineralization was forming. That sounds hard to appreciate, but you got to appreciate how fast these rift structures actually form. It's like being in a down-going elevator as you're busy building up a stratigraphic succession. Down here at Antioch, The mineralization is classic cypress type VMS deposit, so it's hailed cupreous pyrite or copper pyrite. And the succession looks like both Rob McDonald and Carol Evans can see it as mid-ocean floor type, warm type basalt. So deep water setting, depths of at least a kilometer, 1,000 meters, 3,000 feet, water depth or greater, but not less than that to keep chalcopyrite preserved on the ocean floor, preserved, well, from 175 million years ago to present day. So we're looking at over about 200 kilometer strike length of change in water depth from subaerial to shallow to medium depth to dramatic abyssal plain ocean floor type deposits. The question is, can that actually occur? We learn a lot by stepping away from the Eskay rift and starting to look at rift features and studies of rift structures around the globe. And so that's what we're going to do in this section. Then we'll take what's been learned about rift structures elsewhere and bring them back and see if they can help us with our exploration goals in the Eskay rift. Oh, I mentioned Antioch. It's coming up. This, maybe I have to point it. Yeah, I mentioned the Antioch stratigraphy just so you appreciate how different Antioch is from the classic rift fill stratigraphy. I did mention that some places the rift fill stratigraphy may have one of those three characteristic units. I pressed the button twice. Let's see if I can back up. Three characteristic units missing. What's missing here is the rhyolite. There's no rhyolite here. There is a chert unit that's regionally distributed, and as you get closer into the massive sulfide mineralization, and there's I don't know, about 13 massive sulfide lenses, individual lenses in that belt. The double Ed is currently being drilled by Kenrich Eskay. As you move along that chert unit at the contact between the siltstones and the thick succession of pillow basalts, the cherts become pyritic. But anyway, that's the succession there at Antioch, and dramatically different with the sulfides all concentrated right at that chert basalt siltstone interface. So I mentioned, can we see these kinds of dramatic changes in depth along a rift structure? Not only see it, it's actually forming today. We come back again to the Central African Rift. Up at the northern end of it, there's an area called this triple junction called the Afar Triangle, where the rift splits into, I need a little explanation of these red lines. There's two parallel lines here. That's the main rift structure, this arm here. Coming up here, there's a triple junction. One branch goes off to the northwest, another branch heads off to the east. And then there's another parallel rift right along the floor of the Red Sea. In fact, it's the cause of the Red Sea. So I want you to appreciate that what you're looking at here is two parallel rift structures. There's the scale bars 250 kilometers long. What I want to talk about in detail is what's going on along this east arm of the rift, because you start here at this triple junction, and here the rift is trending eastward in a subaerial continental setting. It's desert. You've got two bounding faults of the rift sloping inward at 60 degrees. You've got the rift floor accumulating both lava flows and talus and debris being cascaded down those bounding scarps. You've got those scarps, and you've got a high elevated plateau both to the north and the south of that rift. But as you progress along that rift, you reach a point, there's a thin little blue line there. There's an arm of the Red Sea or Gulf of Aden that comes inland about 50 kilometers from the coast. And then because the floor of the rift is the lowest topographic point, it's heading towards the sea, so the sea fills in the rift floor first. So now you've got a water-filled rift floor. If you come up these scarp slopes, you're still in subaerial setting, exposed to the atmosphere, and of course you've got the escarpments on either side. But as you go further, closer and closer into the coast, you eventually reach the coastline. You cross the continental shelf. The rift structure's still there, but now everything's covered with seawater. You go down the continental slope, and that rift structure, this arm of the rift, merges with this mid-oceanic ridge, which continues along and becomes part of the mid-oceanic spreading ridge of the Indian Ocean, the main spreading ridge that runs through the whole of the Indian Ocean. Let's play that story backwards and start here in the Indian Ocean. You're down here on the abyssal plain. You can see the transform faults cutting across. The mid-oceanic ridge comes along. When it reaches the continent, it propagates up through all this rock that is the eastern part of the African continent, and it has enough momentum, enough energy to continue splitting the continental crust sitting on top of it. So you're actually propagating a rift from the ocean floor right up through this passive continental crust. And I put this 250 kilometer scale bar on there because, of course, that's the length of the Eskay rift. And you can hang one end of that scale bar here in the continental severely exposed material, and that 250 kilometers will take you right through that 50 kilometer long inlet, across the continental shelf, and right down, and that you can reach the open ocean floor in 250 kilometers, and that rift is happening today. It's active today. If it's active today, and this concept that a rift structure is one of the optimal places to be looking for hydrothermal mineralization